All right, let's dive into something that's absolutely critical to our modern world, but happens completely behind the scenes. We're talking about pneumatic pressure testing. Think of it as the invisible guardian that keeps incredibly high-pressure systems from, well, failing catastrophically.
So, picture this. You've got this massive, complex network of pipes and vessels, all designed to handle just immense forces. How can you be 100% sure it's safe? You can't just eyeball it. You have to find a way to hunt down those tiny, invisible flaws, and that is the exact problem we're going to unpack. Okay, so first things first. What in the world is pneumatic testing? Let's break down how something as simple as gas can be used to guarantee both strength and, more importantly, safety.
At its core, pneumatic pressure testing is a non-destructive method, and that phrase right there is the key. It means you can check if a piece of equipment is strong enough and totally sealed tight without damaging it in the process. You're basically using pressurized gas as the ultimate proof test to make sure a system is good to go.
You know, here's the perfect way to think about it. It's just like pumping up a brand new bike tire. You don't just put a little air in, right? No way. You inflate it all the way up to its max recommended pressure. And you do that to find any of those tiny hidden leaks before you take it out for a big ride. Pneumatic testing is the exact same idea, just on a massive industrial scale, where the stakes are way, way higher. Now, what kind of gas you use is a huge deal. You can't just use any old air. For lower pressure stuff, clean, dry air works just fine. But when you get into the really high pressure jobs, nitrogen is the gold standard. Why? Because it's inert, so it won't react with anything, and it's super dry, which prevents moisture damage. And then, for finding the absolute tiniest, most microscopic leaks, you bring out the specialist, a helium mixture. This whole thing sounds like a ton of work, which brings up a really good question. Why bother going to such extreme lengths? Let's get into the nitty-gritty of why this process is so incredibly important.
So this isn't just a friendly suggestion. It's a mandatory, critical safety checklist. Technicians are verifying the fundamental strength of the system, making absolutely sure every single weld and joint is perfect, and confirming there are zero, and I mean zero, leaks. This is all done to certify that the equipment can handle what's called its maximum allowable working pressure, or MAWP, long before it's ever put into service. Every single one of these steps is a defense against disaster.
Now, I know what you might be thinking. Pressurizing something with gas sounds kind of risky. Why not just use water? And that's a fantastic question. Turns out there are some very specific situations where gas isn't just the best choice, it's the only choice.
Right? This is the core dilemma. Using water, which is called hydrostatic testing, is super common and generally safer. But what do you do when the water itself could actually harm the very system you're trying to test?
And this chart breaks it down perfectly. You go with pneumatic, with gas, when the system absolutely cannot have any moisture inside. Maybe it would cause contamination, or rust, or damage some kind of special internal lining. It's also the go-to method when it's physically impossible to drain all the water out afterwards. For these kinds of sensitive, high-pressure systems, gas is the only way to fly. Okay, so we've covered the what and the why. But how is this stuff actually done? Let's take a look inside the meticulous, step-by-step procedure that keeps these high-stakes tests safe. You have to imagine this is all done with almost military precision. It kicks off with a super thorough pre-test assessment. Every plan, every safety protocol is reviewed. Then comes prep. The system is sealed off, and carefully calibrated gauges are put in place. The pressurization part, it's not a race. It's a slow, gradual increase in stages. Then they hold that pressure and monitor everything. After that, they depressurize just as carefully. And finally, every single detail gets documented for the official certification.
But let's zoom in on that pressurization step, because this is really the heart of the operation. They don't just crank the pressure up to max all at once. No, it's done methodically. First, up to 25% for an initial hold, then to 50%, then 75%. And why do they do it like this? Well, these pauses give technicians these crucial windows to inspect the whole system, to listen for any strange noises, and to spot any potential problems long before it ever gets to that final maximum test pressure.
And here it is. This is the number that proves the system's real strength. The final test pressure often goes all the way up to 110% of its maximum allowable working pressure, that MAWP we talked about. Just think about that for a second. They are intentionally pushing the system beyond its normal limits.
It's the ultimate stress test, because if it can handle 110% safely, you can have total confidence that it will perform perfectly at its 100% working capacity. Pushing a system to 110% with a compressible gas, well, that means you are dealing with an absolutely immense amount of stored energy. And that brings us to our final and maybe most important section: how in the world that incredible energy is managed safely.
This quote right here gets to the absolute heart of the risk. Gas can be compressed, which means it stores energy like a tightly coiled spring. To put it in perspective, a vessel at 3,000 PSI holds about 200 times more stored energy with air inside than it does with water. If something fails, that energy gets released instantly and violently. Water, on the other hand, is basically incompressible, so it would just leak out. That massive difference in stored energy is why the safety rules for pneumatic tests are so incredibly strict. So, how do you manage that kind of risk? It's all about layers, multiple overlapping layers of safety. First, they set up huge exclusion zones. Nobody is allowed anywhere near the test area. They often put up physical blast shields as an extra barrier. The pressurization itself, that's all monitored from a safe remote location. Every single little piece, every valve, every fitting has to be certified for high pressure use. And, maybe most importantly, these tests are only ever done by highly experienced pros who have an emergency depressurization plan ready to go at a moment's notice.
And this isn't just some theory. This testing is the invisible guardian for all the critical stuff you see here: the high-pressure gas lines, the wellhead equipment, the compressor skids that form the backbone of our energy industry. The safety and the reliability of all these complex systems, it all comes down to passing these tests.
So the next time you think about all the complex engineering that powers our world, just remember the insane pressure, literally, that it's all under. It kind of leaves you wondering, doesn't it? What other invisible tests and unseen guardians are out there, quietly working around the clock to make sure our modern world keeps running safely day in and day out?